Okay, welcome to Robotics 1. In today's class, I am going to talk about DH parameters and how to use DH parameters to solve some practical problems. So let's start with the example. This is the same problem that we solved in class, and you are asked to work on this problem as part of your quiz. So I'm trying to solve quiz problem 2, and I'm going to solve this problem using DH parameters. So if you remember the quiz problem, the kinematic diagram for this problem can be drawn as something like this. So this is the kinematic diagram for the quiz problem 2. Step 1 is to assign the coordinate system. This is going to be my Z0. This is going to be my X0. Again, this is going to be my Z1. This is going to be my Z2. And we have to follow the 4 rules where X1 has to be perpendicular to Z1 and Z0. So this is going to be X1. X2 has to be perpendicular to Z2 and Z1. So this is going to be X2. Then using the right hand coordinate system, I need to set up the Y's. So this becomes Y0, this becomes Y1, and this becomes Y2. I would add the rotations. This is theta 1, this is theta 2. And I would add some lengths. So if you look at your quiz problem, this distance is considered to be 0. This distance is, I think, A1. This distance is 0. And this distance is A2. Are you with me so far? This is how the kinematic diagram looks for your quiz problem number 2. Now what we have to do is, we have to work out this problem using DH parameters. So for DH parameters, there are 4 rules, and I'm going to give you a shorthand description of the DH parameter rules. So rule number 1, theta is the rotation about Zn minus 1 so that Xn minus 1 is aligned with Xn. So theta is the rotation Zn minus 1 about Zn minus 1 so that Xn minus 1 is aligned with Xn. Alpha is the rotation about Xn so that Zn minus 1 is aligned with Zn. Now, please understand these rules have some sort of similarity. So theta is about Zn minus 1, and which is trying to align Xn minus 1 to Xn. Alpha is about Xn to align Zn minus 1 to Zn. The next rule is to the value of R. R is the distance between the frame n minus 1 to n along Xn. And the fourth rule is D is the distance between n minus 1 to n along Zn minus 1. So this is how you can write these 4 rules in shorthand. And till you remember those correctly, I would recommend that rewrite those rules on the side for each problem so that you will not confuse. Now, check this out. In this case, I have this revolute joint. I have this revolute joint. This is my frame number 0. This is my frame number 1. This is my frame number 2. So when I'm going to draw the DH table. DH table would be theta, alpha, R, and D. So DH table will have theta, alpha, R, and D. And then I would have to have numbers corresponding to each frame. So this is my each joint. Joint number 1, joint number 2. So please note, I have 3 frames, but what I need to do is I need to have number of rows will be less than number of frames. So how do we find out theta? So just for this problem, I'm going to draw the coordinate system separately and show you how to find the values of theta. So first, it may be easier to show the coordinate system 0, which is z0, x0, y0, and the second coordinate system x1, y1, and z1. So these two are the coordinate systems. Now theta is the rotation about zn minus 1. So theta is the rotation about z0 so that x0 gets aligned with x1. So theta is the rotation about z0 so that the x0 gets aligned with x1. But in this problem, x0 and x1 are already aligned. Since x0 and x1 are already aligned, I will have 0. But in theta, you will have to include the joint variable if it's a revolute joint. So this joint is a revolute joint, which means I need to add theta 1. So this is my theta term. Now for alpha, now alpha is the rotation, and I'm going to show it to you one more time here. So alpha is the rotation about x1. So this is the rotation about x1 so that z0 is aligned with z1. The rotation about x1 so that z0 is aligned with z1. In this problem, both of them are actually aligned. So the answer is going to be 0. Next thing is, what is R? R is the distance between the frames. And let's identify the frames. This is my 0th frame. This is my first frame. So R is the distance between the 0th frame and x1 frame along x1. So this is the distance. And that distance is going to be A1. So A1 is that distance. Now D distance is the distance between both the frames along Zn minus 1. So ideally that distance is this distance. But please note this distance is 0. So I'm going to write 0 over here. Everyone understood? That is how you find out the parameters theta, alpha, R, and D. The next thing is we have to move on to the second row. For that, theta again, the theta is between Zn minus 1. In this case, it would be Z1 and Z2. So Z1, Xn minus 1, which is X1, so that x2 and x1, they are aligned. And please note, in this case, x2 and x1 are already aligned. X2 and x1 are already aligned. So this is going to be 0. But it's a revolute joint, which means you have to include the angle theta. So this will become theta 2. Alpha is nothing but the angle between around xn, so that zn minus 1 gets aligned with zn. So zn minus 1 is z1, zn is z2, and please note both of these are already aligned. So value of alpha is going to be 0. And now if you look at the value of r, r is the distance between frame number 1 and frame number 2. So r is the distance between frame number 1 and frame number 2 along x2. So this distance is going to be a2. And please note, d distance is the distance along z1, but that distance is 0. And this is 0 because that is where the robot is. So with this, you have your DH parameter table. And once you have the DH parameter table, what you need to do is you will have to substitute the values in the equation that is like a sort of a black box. Now, some of you may ask me that matrix looks intimidating, but it's not. So I just want to show you a trick. So if you want to find out something like n minus 1 hn, this black box equation can be remembered looking at the similarity of the form. So the first term is cosine theta n, second term is sine theta n, third is 0, fourth is 0. This is the first column of your homogeneous transformation matrix. Second term, this is something similar. So you have sine theta n, cosine theta n. Now check this out. Here you have a negative sign. Sine theta n, cosine theta n. And then what you do is you multiply these by cosine of alpha n, cosine of alpha n, and you place sine of alpha n over here. And now you have 0. Then what you have is you will repeat the exact same thing. So check this out. You will have sine theta n, cosine theta n. However, instead of multiplying it via cos, now you will multiply this by sine. So you will have sine alpha n, and you will have cosine alpha n. And the last term is going to be 0. And if you want to remember the last column, please note it just deals with r. And you'll get Rn cosine theta n, Rn sine theta n, and this comes as Dn and 1. So look at the symmetry of this equation. So you have cosine theta n, sine theta n, minus sine theta n, cosine theta n, and then you have cosine, cosine, sine, and then you have sine, sine, cosine, cosine, sine, d. So this is how you can, this is a trick. Just look at the similarity and then with this equation, we are able to write down 0h1 from this table. So 0h1, the first term is cosine theta 1, sine theta 1, 0, 0, minus sine theta 1, cosine theta 1 multiplied by alpha. The easiest way to try this out is, please note, first time you are going to multiply by cosine of alpha. So alpha is 0. So this becomes 1. This becomes 1. Sine of alpha becomes 0. And this becomes 0. Then you are going to have sine of theta. So sine theta 1. But please note alpha is 0. So this gets multiplied by 0. You will have cosine of theta 1. This gets multiplied by 0. You have cosine of uh, alpha 1. This becomes 0. Then you have a1 cosine of theta 1. a1 sine of theta 1. d1 is 0. This is 1. Please note that this term is 0. This term is 0. And this matrix, the first 3 by 3 matrix, is nothing but the rotation matrix, and the last column is nothing but the displacement vector. And I want you to take a moment to see if this equation corresponds to the same equation that if we were to derive using our regular technique. For an example, if I were to find out 0h1 with the regular technique that we talked, first you will do 0r1, and 0r1, the rotation is about z. So you will have cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Multiplied by, you will have a projection matrix. And in the projection matrix, what's going to happen is, please note that you will have x1, y1, z1. You will have x0, y0, z0. x1 is aligned with x0, y1 is aligned with y0, z1 is aligned with z0. So your 0h1 matrix will be of the form cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0, and you will have 1 over here. Here, the last column, you are going to have distances along x0, y0, and z0. So distance along x0 is nothing but a1 cosine theta 1. So this is a1 cosine theta 1. Distance along y0 is going to be a1 sine theta 1, and distance along z0 is 0 because these two revolute joints are very close to each other. Now, can you see that we got the same equation or same answer using the DH parameters table and the regular technique? For sake of completion, let me find out 1h2. For 1h2, look at the second row. You will have cosine theta 2, sine theta 2, 0, 0. You will have minus sine theta 2. You will have cosine theta 2. Now please note, alpha value here is 0. So you will have 1, 1. You're going to have 0, 0. Then you are going to have sine theta 2, cosine theta 2, but it's going to be sine of alpha. So it's going to be 0, 0. You will have 1 here. You would have 0. And R is A2, A2 cosine theta 2, A2 sine theta 2. You're going to have 0 and you're going to have 1. So, okay, there is a question. I'm not going to answer this question right now because let me finish this problem. I don't want to confuse myself and confuse you. Let me finish this and then I'll answer your question if you don't mind. So now 0h2 is equal to 0h1 multiplied by 1h2. And please note that the answer that you will get will be the same as before. Okay, I will repeat this one more time. I'm gonna teach you DH parameter technique because that is sort of a de facto technique that is used in all the robotic textbook. But I do not recommend using DH parameter technique And the reason for that is there are cases where the DH parameter technique fails. And I will take an example where DH parameter technique fails, and I'll tell you why it fails. So I would strongly recommend to stick to bare bone basic method that I showed you for constructing the homogeneous transformation matrices. Even though that method may not be widespread or discussed in all the textbook, that method always works. So let me take one more problem. So in today's class, I will try to solve some problems with DH parameters so that you understand how this technique works. Please note, at the end of the day, this is sort of a black box technique, wherein once you have this table filled out, you just use this equation in front of you and plug and chug and get homogeneous transformation matrices. But if you are not careful, you will get totally wrong answers. And we will work out that problem where DH parameter technique fails. I don't think, I don't know. I usually prefer the regular technique because I will show you the cases where the DH parameter technique does not work. Then there is something called as modified DH parameter technique. If you want, you can refer to the references in our textbook where they mention about the modified DH parameter technique. But I'll show you how this technique works, because all the robotics textbooks that I have seen, they tend to use the DH parameter technique. But let me take one or two problems so that we are comfortable with DH parameter technique. Any questions before I proceed to next problem? Okay. And if you have any questions, I will answer those questions after I work out the problem. So next problem is problem 1 from the quiz. So problem 1 from the quiz. I will show you the kinematic diagram, and please note, depending upon your interpretation of the problem, your kinematic diagram may be slightly different than my kinematic diagram. So I know some students consider that to be a 2 degree of freedom robot. Some students consider that to be a 3 degree of freedom robot. Whatever degree of freedom robot you considered, as long as your kinematic diagram and your forward kinematics is consistent, you will get full credit. So I will show you the kinematic diagram that I constructed. So I assume, I considered the most difficult case, because there were students who considered it to be a 3 degree of freedom robot. So I will solve this as a 3 degree of freedom robot. 2 degree of freedom robot is a simple subcase of this 3 degree of freedom robot. So this is the robot that I have considered. This is my first revolute joint. Then this is the second prismatic joint, and this is the third prismatic joint. So this is RPP robot. And what I'm going to do is, according to our technique, I'm going to assign Z0, Z1, and Z2. And I'm going to add one last to Z3. This is my end effector. To my end effector, I will add Z3. Now I would add X0. I would add Y0. I would add X1. I would add Y1. Then I would add X2. And I would add Y2. And once again, I would add X3. And I would add Y3. Now I want you to check if all the 4 rules are satisfied. X1 is perpendicular to Z1 and Z0. X2 is perpendicular to Z1 and Z2. x3 is perpendicular to z3 and z2, x1 intersects z0 and z1, x2 intersects z1 and z2, x3 intersects z3 and z2. Not only that, you will see that it's a right hand coordinate system, and I would add the distances, and these are the values that I assumed. A1, this is the joint variable, so I'm going to call this D2. This is the fixed variable, so I'm going to call this A2. This is the joint variable, so I'm going to call this D3. And I'm ready to solve the problem. Do you want me to write the 4 DH rules in shorthand? Just for this problem, I will write this down. The first rule is theta is the rotation. So rotation about Zn minus 1 so that Xn minus 1 is aligned with Xn. Alpha is the rotation about Xn so that Zn minus 1 is aligned with Zn. R is the distance between frame n minus 1 to frame n along Xn. And last but not least, D is the distance between n minus 1 to n along Zn minus 1. This is the shorthand representation of the 4 rules. So let's fill in the table. So I have 3 frames. Actually, I have 4 frames, 0, 1, 2, and 3. So I'm going to have 3 rows. So this is going to be theta. This is going to be alpha. This is going to be R. This is going to be D. So let's start with joint number 1. So theta is, and again, let me add the joint variable here. This is theta 1. Theta is the angular orientation about Zn minus 1, which is Z0, so that the Xn minus 1 is aligned with Xn. Xn minus 1 is X0, Xn is 1. Both of them are already aligned. So I will have theta is 0 plus theta 1. Alpha is the rotation about Xn, so that Zn minus 1 gets aligned with Zn. Please note Z0 and Z1 are already aligned, so alpha is equal to 0. R is the distance between 2 frames, and I will show you the locations of the frames. This is frame 0 and frame 1 along Z0. Along Xn. That distance is 0. And D is the distance between frame 0 and frame 1 along Zn minus 1. So that distance is A1. Now I will go to the second point. So in second row, I have to find out the value of theta. Again, theta is the rotation about Z1 so that the Z2, so that the Z1 gets aligned, X1 gets aligned with X2. Please note that X1 and X2 are already aligned. So this angle is nothing but 0. Please note that there is no revolute joint. It's purely prismatic joint. So there is not going to be any angle theta. Let's look at alpha. Alpha is the rotation about Xn. Xn in this case is X2. Rotation about X2 so that Z1 gets aligned with Z2. Z1 gets aligned with Z2. So I have to write this down. So check this out. This is Z1 and this is Z2. And only way Z1 can get aligned with Z2 is by rotation of -90. And I want you to take a minute to notice that there is a negative sign here. And the negative sign is here because rotation is about x2. But what we are rotating Z1. So Z1 needs to be rotated in 90 degrees in the negative direction so that Z1 gets aligned with Z2. So please note, I need to write down here. We are rotating Z1 around x2 so that Z1 is aligned with Z2. Thus, the rotation is -90 degrees. Everyone understood this? And just if you need, you can just curl your fingers around the rotation and see if it is indeed -90. The next thing is we have to find out the value of R. Value of R is the distance between two frames, and the two frames that we are considering here are the frame number 1 and frame number 2 along x2, and this distance is a2. And the last is the distance between n-1 to n along zn-1, which is along z1, and this distance is d2. And the next, last but not least, is we need to finish number 3. And this number 3 is what you do is again value of theta. Theta is zn-1. So we are looking at z2. So a rotation about z2 so that x2 is aligned with x3. Please note that both of them are already aligned. So I have a 0. Alpha is the rotation about x3 so that the z3, so that the z2 gets aligned with z3. It's already aligned. So I have 0. R is the distance along x3 between the frame 2 and frame 3. So this is going to be 0. And the last distance is the distance between two frames along zn-1, which is z2, and that distance is d3. So now what we have is we have this table. And now what you need to do is plug and chug. So, but please note, whenever you are plugging the values in, whenever you are plugging the value for theta 1, you need to include this entire value. You need to include this entire value. You need to include this entire value along with its signs. So what I'm going to do is just quickly for my reference, I'm going to write these matrices down and you can correct my answers if I'm wrong. So 0h1 is going to be cosine theta 1, sine theta 1, 0, 0, minus sine theta 1, cosine theta 1. And the reason for that is alpha is 0. This is 0. This is 0. You get 0, 0, 1, 0, 0, 0, A1, 0. Actually, this is what you get. And please check this answer with your regular technique. This is, I use the DH parameter technique. What I did, I used the first column and plugged the values in this equation, which is for homogeneous transformation. Next is 1H2. For 1H2, the angle is theta 2, but please note it's a prismatic joint. There is no revolute joint, so there is no theta. So it's just going to become 1 because it's cosine of 0, sine of 0, 0, 0. Then you are going to have sine of 0. Then you are going to have cosine of 0. That is going to be 1. That gets multiplied with sine of 0. So get 0. You get minus 1. You get 0 here. You get 0. You get plus 1 here. You get 0. You get 0. And the last but not least, the theta 2 value is 0. So A2, 0, D2, 0. This is what you get by plugging in DH parameters. And 2H3, this becomes very simple. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, D3, 0. And 0H3 is 0H1, 1H2, 2H3. Any questions on the DH parameter technique? Oh yeah, the last one is 1. The last one is 1. Any questions on the DH parameter technique? Going once? Going twice? No questions? So what do you think? DH parameter technique is simpler than the technique that we discussed earlier? I'm looking at the chat window. Oh, yes. Mr. Chin has a question. Do you want me to unmute you or can you type? Unmute. Yes, Mr. Chin, you're unmuted.
So I just have a quick question. So all these values that you got for the the OH1, the 1H2, you got all these from the table from the third slide, right?
Yes. And I took those values and plugged in the equation on the second slide. Can you see the equation?
Yes.
The only thing you have to be careful is when I say theta n, whatever you have at that location, it could be 90 plus theta 1 or minus 90 plus theta 1 or whatever it is. The whole thing has to go in there, not just theta 1. You see what I'm saying?
Yes, I see it. Thank you.
All right. Okay. Let me take one more problem. And yeah, for this problem, yeah, Andrew, try to run with a computer program. That would be fine. But you will see that there are some tricks. So in few cases, it doesn't work. Let me take the case. Let me take one problem where the DH parameter technique works. Okay. So let's take problem 3 from your quiz. The problem 3 from your quiz is called as the SCARA robot. SCARA robot. So how do we solve this problem with the DH parameter technique? So let me draw the kinematic diagram. The kinematic diagram looks like this. and you have this prismatic joint. So the Skira robot is revolute. You can make it 3 revolute. If that's what you assume, that's totally fine. The process will be the same. So there is a question, is would it be, are there 3 revolute joints? Well, if you assume that robot to have 3 revolute joints and a prismatic joint, that's totally fine. The process is not going to be different. You just have one more homogeneous transformation and one more angle. Okay, now let's start with setting up the coordinate system. Z0, Z1, but please note, in this case, I'm gonna say Z2. And please note, the rules say that Z has to be aligned with the direction of the joint variable. It doesn't say that it should correspond to the direction. In a sense, like Z has to be aligned with the joint variable, but you can consider Z2 to be going upwards even though your joint variable is going downwards. You see what I'm saying? So basically my Z2 is going upwards, but the joint variable or the extension of the Skira robot is going downwards. Okay, so what I'm gonna do is I'm gonna add my other coordinates, x0, then I will have y0, then I will have x1, I will have y1, then I will have x2, I will have y2, and then at the end, well, I can actually add just one more, just like this. So I can say this is x3, c3, y3. And now I'm going to add the distances. The distances are a1, this angle is theta 1, this distance is a3, this distance is a2, this distance is a4, and this distance is d3. So this is how the setup is. Now please note, there are this is the 0th frame, this is the first frame, this is the second frame, this is the third frame. Now what I'm going to do is, one last time I'm going to write down the rules in shorthand. One last time. I will write the rules again in the next problem too. So theta is the rotation about Zn minus 1, so that Xn minus 1 gets aligned with Xn. Alpha is the rotation about Xn, so that Zn minus 1 gets aligned with Zn. R is the distance between n minus 1 and n along Xn, and D is the distance between n minus 1 and n along Zn minus 1. These are the 4 rules. And now I'm going to draw the table. So you're going to have theta, you're going to have alpha, you're going to have R, you're going to have D. Theta, alpha, R, and D. So joint 1, theta is the, you have to look at Zn minus 1, so which is Z0, so that X0 and X1 are aligned. So the joint variable is theta 1. So this is 0 plus theta 1. Alpha is the rotation about X1 so that the Z1 and Z0 are aligned. But please note they are already aligned. So you have 0. R is the distance between frame 0 and frame 1. R is the distance between frame 0 and frame 1 along X1. And please note, when we say along X1, the distance is positive. Please note, the distance is positive. Actually, sorry, distance X, distance is negative. So this distance is minus A2, because please note the distance is from 0 to 1, but the direction is in this direction. So this distance is negative. And D is the distance between the frame 0 and frame 1 along Z0. That distance is positive, which is A1. Now next thing is frame 2. For frame 2, theta is the distance between Z1, around rotation about Z1, so that X2 and X1 are aligned. Please note they are already aligned, so this becomes theta 2. Alpha is the rotation about X2 so that Z1 and Z2 are aligned, so they are already aligned, so you have 0. R is the distance between frame 1 and frame 2. So please note where is frame 1 and frame 2. Frame 1 is here, frame 2 is at the location 2. And R is the distance along X2. That distance is minus A4. And the next thing is the distance D is D3. Sorry, this is A. This distance is A3, and that distance is positive. The last but not least, for third, please note it's a prismatic joint. There is no rotation, but so theta is the rotation between Zn minus 1 around n minus 1, so that xn minus 1 and xn, they are aligned. So x2 and x3, they need to be aligned. And please note they are already aligned, so this has become 0. Alpha is the rotation about x3 so that z2 and z3 are aligned. They are already aligned, so this distance is 0. R is the distance along x3 so that the frame number 2 and frame number 3 are already aligned. But if you look at the way the frames are, they are already aligned. There is no x offset, so this is going to become 0. And last but not least is the distance between z the axis around Zn minus 1. Please note these two are apart by D3, but D3 is going in the opposite direction of xz2. So I need to write this down here. A side note, D is distance between frame 2 and frame 3 along Z2. Thus, it's minus D3. So, and now we have our parameter table done. And once the parameter table is done, what I should be doing is I should go ahead and construct my homogeneous transformation matrices with the formula that we talked about with this equation. And this equation gives me 0h1 is equal to cosine theta 1 sine theta 1 minus sine theta 1 cosine theta 1 0 0 0 0 0 0 1 0 minus a2 cosine theta 1 minus a2 sine theta 1 a1 0 1 h2 cosine theta 1 minus sine theta cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 0 0 0 0 0 0 0 0 1 0 minus a4 cosine theta 2 minus a4 sine theta 2 0. So this is a3 1. And the last but not least 2h3 1 0 0 0 0 1 0 0 0 0 1 0 0 0 minus d3 1. And 0h3 is 0h1 1h2 2h3. Okay, all right, so everyone understood the homogeneous transformation technique using DH parameter? How many of you are still in favor of DH parameter technique? Going once, going twice? Oh, it's not bad as long as you know how to use it. What was the value in the table D for frame 3? Minus D3. Oh, wow. Okay, I wish I could go over the technique. Let me try to finish one more problem. Let me work out one more problem. And I would caution you, in this problem, the DH parameter technique does not work. And I will tell you the reason why. Okay, it may be faster. That doesn't mean it will give you the right answer. Okay, let's look at problem 4. This is the same problem from your quiz. So this is my kinematic diagram. And now this is the robot. So you have the revolute joint, you have the prismatic joint, you have the revolute joint. This is the kinematic diagram. I'm going to assign the coordinate frames. Check this out. This is Z0. This is Z1. This is Z2. Okay, Z0, Z1, Z2. Now let's go step by step. First, I'm gonna write down X0. X0 has to be perpendicular to Z0 and the previous Z, which is Z minus 1. But there is no Z minus 1, so it doesn't matter. X1 has to be perpendicular to Z1 and it has to be perpendicular to Z0. It needs to intersect Z0 and Z1. Now please note, in this problem, the only way that can happen is if I were to draw something like this. However, in this particular problem, X1 is actually parallel to Z1. It doesn't intersect. So X1 is not intersecting, X1 is parallel to Z0. So which means we have to shift, we will have to shift the coordinate system to match the orientation, and we will do that. The next thing is I have Z2 over here. So what I'm going to do is I will try to find out X2, where X2 is perpendicular to Z1 and Z2 and X2 is intersecting Z1 and Z2. And then I will draw the Y1s. This is going to be my Y1 and this is going to be my Y2. And I will use the same trick that the last coordinate system is same as the coordinate system before. So I will have Z2, Z3, Y3, X3. Everyone is okay with my kinematic diagram? Coordinate systems make sense? The only thing what I will have to do is, please note, and I need to write it down, X1 does not intersect Z0, so we have to translate the frame. So since X1 does not intersect with Z0, we will have to translate the frame. Depending upon what you follow, you can have translation multiple ways. You can actually place this frame all the way on top of here. So you could have, I'll use a different color. So you can use, you'll say this is going to be my Y1. This is going to be my Z1. And this is going to be my X1. You can translate, yeah, X1, yeah, X1 can be placed, no, if you place X1 going up, then it will be parallel to, so you will actually, if you place X1 going up, then it will violate two conditions. That means X1 will be parallel to Z0 and X1 will not be intersecting with Z0. The way I have drawn this is X1 is parallel to Z0, but X1 is at, when X1 is perpendicular to Z0, but X1 is not intersecting with Z0. So Alejandro, to answer your question, if we were to do X1 along vertical line or going up, then it will violate two conditions. Here we are just violating one condition. So this configuration is better. Okay, moving on. Now we need to construct the DH parameter table. And DH parameter table, I am going to draw, this is one revolute, prismatic revolute. So I need to have theta alpha, then R and D. Now here, let's start from the beginning. So first, rotation joint is theta 1. This distance is A1. This distance is A2. This distance is, I'm gonna call D2. This distance is A3. This distance is A4. Okay, so first and foremost, I need to, theta is the rotation about Z0 so that X0 gets aligned with X1. And as you can see, my X1 is here. My X0 is here. So theta is going to be 90 plus theta 1. Do you want me to write the rules, or are you comfortable me not writing the rules? Theta is the rotation about Zn minus 1 so that Xn minus 1 gets aligned with Xn. So theta 0 needs to get aligned with X1. But please note, these two frames are on top of each other. So here, the way we are showing is just the orientation. Alpha is the rotation. Alpha is the rotation about Xn, which is X1, so that Z0 gets aligned with Z1. The only way that rotation is possible if I were to have alpha as 90 degrees. Because check this out, you have X0, Z0, Y0, and I'm gonna show you this is X1, this is Z1, and this is Y1. So the only way I need to find out the rotation about X1 so that the Z0 gets aligned with Z1, and that is the rotation 90 degrees about X1. Now R are the distances. Since these two frames coincide, this distance is 0, this distance is 0. Now moving on to frame 2. Now I'm interested in finding out the rotation between frame. It is now I have to look at the translated frame 1. So this is between translated frame 1 and frame 2. So look at frame 2. Frame 2 is over here, frame 2, and translated frame 1 is over here. So translated frame 1, so 1T, I'm gonna call 1 translated, and you have frame number 2 over here. So the rotation is about Z1. Locate where is my Z1? Z1 is along the horizontal line. The rotation around Z1 so that the X1 gets aligned with X2. The rotation along Z1 so that X1 gets aligned with X2, that is 180 degrees. And please note, my X2 is here, my X2 is here, my X1 is here, and I have to rotate X1 so that it's get aligned with X2 around Z1. So please note, this is something that I'm gonna do. So I need to rotate x1 around z1 so that I get aligned with x2. So that gives me 180 degrees. Now I need to look at rotation about x2 so that z1 gets aligned with z2. So for z1 to get aligned with z2, this rotation has to be 90 degrees. Now r is the distance between 1t and frame number 2 along x2. So 1t and frame number 2 along x2. Now please note that these two frames, they are in the same plane. So there is no x2 distance between these two. So that distance is going to be 0. But let's look at the distance between frame 2 and frame 1 translated around Z1, and that is A2 plus D2. And that is what you have for the second. Now let's look at the last column. So far so good. In the last column, I have number 3. So number 3 is the relationship between the frame 2 and frame 3. The good news is, and I want you to pay attention here very carefully, that these frames are aligned like this. So check this out. I just want to show you these frames separately. You have Z2, Y2, X2. You have Z2, Y2, X2. And you have Z3, Y3, X3. So essentially what it means is these two frames are sort of aligned. So when these two frames are aligned, let's go back. Theta is the rotation about Z2 so that X2 and X3 get aligned, and this value is 0, but there's a joint, so I need to add, so theta 3. So there will be theta 3. Now alpha is the rotation about x3, so that z3 and z2 gets aligned, and this is 0. Now r distance, and this is very important, and I want you to look at this equation very carefully. R distance is the distance between frame number 2 and frame number 3. R is the distance between frame number 2 and frame number 3 along x3, and that is 0. And D is the distance between frame number 2 and frame number 3 along Z2, and that is A3. Are you with me so far? Everybody understood what's going on? This problem became unnecessarily complex because we had to translate the frame and then rotate, use the DH parameter. Okay, there is a big mistake in this formulation. Can someone tell me what are we missing? There is something majorly wrong in this formulation. No, not distances. Correct. A4 is not available to us. Now I want you to verify. Everyone, please pay attention. A4 is missing. There is no theta 2. A1 A1 is missing. Now, if you were to look at the problems that you worked out using the technique that we discussed, you would realize that that solution, the forward kinematic solution, will have A1 and A4. So if you work out, and I need to write this down, if you work out problem 4 using rotation matrix technique, forward kinematics will contain A1 and A4, but with DH parameters A1 and A4 are missing. And that is the biggest drawback of the DH parameter technique. What it means is when you use DH parameters, any dimension along y-axis is neglected. So that's why I do not recommend using DH parameters. So some of you may say, hey, then how come everyone is solving the problem with DH parameters? Because what they do is, when they construct their homogeneous transformation and axes, they construct the axis in such a way that the important dimensions of robot do not fall along y-axis. In some cases, it's possible to orient the matrix, the coordinate frame, so that the important dimension of robot do not coincide with y-axis. It could be y0, y1, y2, but it may not always be possible. So whenever you are using the DH parameter, the major limitation of the DH parameter technique, even though it may look simple and plug and chug, if the robot has any dimensions around y-axis, that dimension will be neglected, which means your forward kinematics would be incorrect. And what you will have to do is you will have to go back and revise your coordinate system and kinematic diagram to make sure that your dimensions somehow either appear in R or appear in D. If your robot dimensions do not appear in R because they are not along XN, or if they do not appear along D because they are not along Zn-1, your forward kinematics will be incorrect. So that's why I would recommend sticking to the technique that we discussed in class. But as a roboticist, you should be familiar with DH parameter. Also, you should be familiar with the limitations of the DH parameter technique. And that's it. I'm gonna stop here. Today's lesson is super important because your next quiz, I'm gonna give you problems and I'm gonna ask you to solve with DH parameters. And if you are not able to solve with DH parameters, then you should be able to answer the question why, and then you should be able to work out the problem with the regular technique. And that's it for today. I'm gonna stop here. I will see you on Tuesday.